All right, let's take on this second of two goodness of fit problems that are in your mastery problems and solutions sections this time. I mentioned in the previous video that I was going to use the calculator in order to affect the solution to this problem. But I also mentioned there was a little bit more to this problem, and that's actually what's going to take the time here. You're going to find that the goodness of fit problems, often the most difficult part about them is trying to decide what the expected or theoretical distribution ought to be. So some of the problems give you the expected distribution, give them to you directly. Some of them give you some information, you've got to deduce it, and that's the case here. I like this problem. This problem says, are these dice loaded? And what it does is on 1,000 rolls of two dice, it gives you the distribution that was observed of the sums of the two pips that come, the two sides that come up. And there it is. So the question is, what are we going to compare that to? Because if the dice are not loaded, if they are fair, yeah, then it ought to follow, the dice ought to follow some theoretical distribution. If they are not, well, maybe you have some evidence here in this sampling distribution that maybe it's not. You can tell by running a goodness of fit test and seeing if this sampled or observed distribution follows the theoretical. So, okay, how are we going to do that? Let me first sort of switch gears around here. We've got some calculations to do. And in order to figure out what this distribution is, you have to kind of turn your head back quite a few chapters to the chapters in which we were dealing with discrete probability distributions, right? A discrete probability distribution is a value for a random variable, and against that value it's a probability of occurrence of that value. So how the heck do we do that? I won't torture you very long. The answer is, let's go make up this matrix where you've got die 1 down the side and its possible values 1, 2, 3, 4, 5, 6, and die 2 along the top and its possible values 1, 2, 3, 4, 5, 6, and inside you've got the sum. So against 1, 1 you've got 2, against 1, 2 you've got 3, against 1, 3 you've got 4, and so on and so forth. And if we just do a little multiplication, you can see that there's 36 values. There's 36 different outcomes of the sum when two dice are rolled. That's got to start to sound familiar. So if you want to know how many ways the sum 2 can come up, you just have to look and scan through the table, and it's pretty clear that it can only come up one way, and that's when die 1 and die 2 are both 1. So the probability of that happening is 1 out of 36, right? 1 is the number of ways that the sum 2 can come up. 36 is the total number of outcomes in the sample space. God, I love to talk like that. Okay, how about the sum of 2? Well, that can come up 1, 2, or 2, 1. Did I say that right? The sum of 3 can come up 1, 2, or 2, 1. You would expect there to be 2 ways out of 36, probability that is 2 36. Likewise, if you just look in the table, how many different ways can the sum of 4 come up? It can come up 1, 3, 3, 1, or 2, 2. And sure enough, there's 3 4s in that table out of 36. Probability is 3 out of 36. So if I just kept doing that, I could fill out the rest of this table. And what I would have is not quite what I need, but darn close. What I have now is the distribution of the probabilities, right? Which maybe we could use, maybe we couldn't use, but if you look above at the observed sums are a number. They're a frequency, they're a count. And here with the probabilities, we're dealing with a relative frequency. So I've got to convert one into the other. And all I really have to do to see the theoretical distribution of 1,000 rolls is multiply that probability by 1,000, and that would get you the expected values. So if I do that on the next page, 27.78, that is just 1,000 times 36. 55.56, that is just 236 times 1,000, and so on and so forth. And so therefore, That is the expected values. That's the answer to the first part of this problem. And that's the theoretical distribution that we're going to compare against this observed distribution. And how are we going to do that? Well, before we start, let's write down the null and alternative hypotheses. This is an easy part because for the goodness of fit, the null hypothesis is always that the observed distribution is consistent with the expected distribution. Now you might translate in the context of this problem to null hypothesis. These are fair. The die are fair. Okay. The alternative hypothesis is these dice are loaded. All right. That is that the observed distribution does not follow on. So what I've got to do now is let me fade out and let me switch this back in, and I'll run through the calculator operations. Right. All right. So let's make use of the calculator here now. I better turn it on to begin with. I've actually already preloaded it because there's no real educational value in watching me fill out lists. But just to show you, let me go to stats. I'm really going to stats. There, I'm in edit. Let me go to edit, and there's my two lists. The observed list is in list 1, and I'll just read off these numbers: 22, 51, 60, 101, 126, 175, 165. And if I was to scroll down, you would see the rest. In L2, the theoretical list is there, and those numbers were 22.78, 55.56, 83.33, 111.1. So I've already preloaded this thing. So that's sort of the end of your input at this point, really. So far you've picked edit, you've loaded edit, and now the last thing you have to do is go back to stat. Goodness of fit is a test, so we're going to go over to tests. We're going to go down and find chi-squared goodness of fit. When we get to chi-squared goodness of fit, we're going to open it, and it's going to ask me where's the observed, where's the expected. As I just showed you, they're in L1 and L2 respectively. And what's the degrees of freedom? Well, we've got sums from 2 to 12, meaning that we've got 11 different sums, and the degrees of freedom are the number of categories, the number of sums, minus 1. So it's 11 minus 1, or 10. That's why you see 10 entered in here. Let me bop down to calculate. And look, immediately it gives you the chi-square test statistic if you wanted it. And maybe more importantly for our purposes, it gives you the p-value 0.011. And since we're dealing with a level of significance of 0.05, p is less than that level of significance, you reject the null. These dice are loaded. All right, thanks a lot.